in the lecture series of Discrete Structure and Theory of Logic. I am Pransu Saxena, Assistant Professor, Department of Information Technology. And today's topic of discussion is transitive relation and equivalence relation. These are very important relations. We are studying topic. It's called relation in discrete structure. So let's start the definition of transitive relation. Suppose we have set A, which contains three elements, 1, 2, 3. And a relation R, which is the subset of Cartesian product, is defined on set A. Then this relation R is said to be transitive relation if and only if it satisfies following property. And the property is if any element A which is related to any other element which is B and B is also related to C. This implies that A should be related to C. Or in other words, we can say that any ordered pair A comma B is a part of relation and B comma C is also the part of relation. This implies that A comma C should also be the part. Remember, this is a conditional statement. We have already discussed about this conditional statement in the previous lecture. Let me define again what is the meaning of this conditional statement and in what cases this condition will become. So suppose in any relation, A comma B is present and B comma C is also present. That means this entire condition is true. And this is also true. That means in that relation, A comma C is also present. So the whole statement will become, that means whole equation, whole relation will become true. Now, if the very first statement is present, that means A comma B is the part of relation and B comma C is also the part of relation, but A comma C is not the part. That means that condition is not transitive relation. And or say this condition is not satisfied and hence the relation is not. If I again say the very first condition is false, that means A comma B is not part of relation or B comma C is not the part of relation or both are not the part of relation. So in that case, whether this condition is true or false, it's really not matter if the very first condition is false. So whether second condition is true or false, it's really not matter. The ultimate equation will become true. So that means the relation will become. Let me give certain example. Suppose a relation R, which is defined on set A, is say empty set. So whether this relation is transitive or not, to check. So in this relation, A comma B is not present, B comma C is also not present. So that means this condition will become false. When this condition will become false, so ultimate the answer is true. So that means this relation is transitive relation. Let me give another example. So I will rename this equation as R1. So let me give another example. R2 relation is A cross A, which is a Cartesian product. If you don't know the definition of Cartesian, that you can refer my previous video. So R2 is a Cartesian product. Cartesian product means which contains every possible order. So that means for every A comma B, B comma C exists, and for every A comma B and B comma C, A comma C exists. Because this Cartesian product contains every possible order. So this relation is definitely will become a transitive relation. Let me try another example, say R3, a relation which contains ordered pairs, say 1, 2, 2, 1, and 1, 1. Now check whether this relation is transitive or not. So Remember this equation, A comma B. We have to search out B. So if B is present, then we have to check whether A comma C is present. Fine. So 1 comma 2. So A comma B. Now we have to search order pair which start from B, that means which start from 2. So A comma B, B comma C. Now A comma C, A will become this and C will become this. So okay, whether 1 comma 1 is present in the relation, yes, 1 comma 1 is present. So this ordered pair will justify this relation is started. But we need to check again for another ordered pair, because every this relation said for every A comma B, if B comma C exists, then A comma C should also be exist. So A comma B can be any ordered pair. Now we have to check for another ordered pair also. 2 comma 1. Any ordered pair which start from 1? Yes. 1 comma 1. So 2 comma 1, 1 comma 1. Whether 2 comma 1 is present? Yes, 2 comma 1 is. But we have to check also 2 comma 1 is present, 1 comma 2 is present. That means 2 comma 2 should also be the part of that relation, but this 2 comma 2 is absent. So that means this relation is not transitive relation. So there can be n number of examples by which we can test whether a relation is transitive or not. So there can be a phenomena which is called relational matrix, by which can check whether a relation is transitive or not. And this phenomena can be solved with the help of relational matrix. Relational matrix. Usually, we represent this relational matrix with the help of MR, where M stands for matrix and R stands. So how we make this MR? We will give certain examples. Suppose we have a set A which contains 3 elements, 1 comma 2 comma 3, and a relation R on set A, which is written as say 1 comma 1, 1 comma 2, and 2 comma 1. Now we have to check whether this relation is transitive or not. Because suppose we have a very large equation, cannot check for every ordered pair possible. We cannot verify whether this relation is transitive. So we need to we need to have some methods by which we can check whether any relation is transitive or not. So if I talk about this relational matrix, which is MR, MR contains the list of every ordered pair present in the list. So row represent the element of set. So we have 3 elements in set. Element number 1, element number 2, element number 3. So this 3 element will become row, and also these 3 element will become. Now, any ordered pair which present in relation will be treated as 1, as any ordered pair which is absent in relation will be treated as. So in this relation, 1 comma 1 is present, so this will become 1. In this relation, 1 comma 2 is present, so this will become 1. In this relation, 2 comma 1 is present, so 2 comma 1, 2 comma 1, row number first, column number second, so this is. Now rest ordered pair is absent, so we need to write all G. So this is just a representation of relational matrix. Now the formula is if MR square plus MR is equal to MR, if this following equation is satisfied, then the relation is said to be transitive. If this relation is not satisfied, then relation is not. So let me check for this example. So this is my MR. This MR squared is nothing but just a dot product. We have to apply a logical and logical OR gates. That means if First input is 0, second input is 0, and we are doing just multiplication, then answer will become 0. If first element 0, second element 1, the answer will become 0. If first element 1, second element is 0, the answer will become 0. If first element 1, second element 1, the answer will become. This is logical AND. If we talk about logical OR gate, then we need to apply 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 1. So this is logical OR. These two tables we need to apply to solve this formulation. So remember this MR, write it again. MR is equal to 1, 0, 0, or this is 1. So 1, 1, 0, 1, double 0, and 0, 0. This is my previous. We need to calculate MR square. That is MR dot MR. So 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, double 0, 0, 0, 0. If I apply dot product between these two, so first part we will solve. So this one multiplied by this one, this plus this one multiplied by this one, plus this 0 multiplied by this 0, and this element. So if I solve, if I do multiplication, so multiplication will be like the column of first matrix multiplied by row of another. So this will become 1 dot 1 plus 1 dot 1 plus 0 dot 0. Ultimate answer is 1. Likewise, this will be multiplied by this. So this 1 will become 1. This will be multiplied by this. So this will become 0. Again, this 1, 1, 0 multiplied by this. So this will multiplied by this. So this will become 1. And this will multiplied by this. So this will become 1. And here is all zeros. So this is my MRS. And the what is formulation? Formulation is MR square plus MR. So if I add, this is my MR square. If I add this MR square into, if I add this MR square in a MR, so the formulation will become like this: 1, 1, 0, 1, 1, 0, 0, 0, 0, plus what is my previous MR? 1, 1, 0, 1, 0, 0, 0, 0, 0. And the ultimate answer will become like this. So 1 plus 1 will become 1, 1 plus 1 will become 1. This is 0, this is 1, this is 1, this is 0, this is 0, this is 0. This is 0. So this is MR square plus M. Whether this is equal to MR? No, this is not equal to M. So this is not equal to M. So the condition is not, say, transitive. We have already checked this here. So this is not a transitive relation. And this here we have also proved this is not a transitive relation. So thank you so much for this transitive relation. In the next lecture, we will discuss about equivalence relation. Thank you.